Okay, welcome back everybody. This is the last of the three examples we're going to be looking at in this playlist. This example is the damped harmonic oscillator. Here's a schematic diagram of the system we're talking about. It's a one-dimensional system, only moves in the x direction. It's a mass that we're looking at, and it's attached to a spring and also to a dash pot, which provides a damping. So this is a spring mass damper system. Again, the states that we're interested in are only the position and velocity, and we're going to derive the state space model from the differential equation. We won't show you the full derivation of how that's going to be done. That's done in a later videos in another playlist where we'll be talking about state space concepts. So the result is, once you map it into the state space model of dimension 2, the answer is a matrix exponential for phi, the state transition matrix. We'll explain how to calculate that a little bit later, but and also, like I said, in the state space concepts playlist, we'll talk about how you actually derive the state space model itself and the solutions. Also note that we're using J for the time step index. K is already being used for the spring constant, so we're avoiding a clash there. And the measurement model is exactly the same as it was before. This is certainly something that you can play with in the Python script to add additional measurements, or perhaps to add a different measurement source like a velocity sensor. If you're interested in finding out how that's done, let me know in the comments and I can certainly create a video on that. Alright, so as mentioned before, the state transition matrix is right here, and it can be approximated through a series expansion, or you can take the easy way out, which is what I've done in the Python scripts, and just plug the parameter values into the matrix and call the SciPy matrix exponential function. Because phi and q are matrices, the state and covariance extrapolation equations do not simplify from their matrix form, but we'll carry out that matrix math in the next slide, so you can see how it comes out. Also, like phi, q is dependent on delta t, and moreover on a parameter q, which represents the continuous process noise variance. Now, you don't know what that is because we haven't talked about continuous state space models, but in the next playlist we'll be getting into that. But it's very important to realize that this is dependent on delta t and this other parameter q, which is a constant for our simulation purposes. The details of how this model is derived from the continuous model can be found in the excellent book by Grewal and Andrews. Okay, so let's carry out the covariance extrapolation equation. In our case, two-dimensional case, it looks like this. It's phi p, phi transpose plus q. Carry out the math for the first matrix multiplication, you get something that looks like this. And then you can simplify that once you apply the fact that we know that phi 1, 1, the first element of phi in the upper left-hand corner, is actually 0. So that helps us simplify the calculation and makes it fit on one slide. We've also decluttered, as before, the superscript pluses on the right-hand side and also the j-1 indices. Kalman gain is just as before, nothing new here. In fact, this is an answer to the last question, which I left as an exercise to the reader or the listener in the last video that we did on constant velocity motion. Again, we're suppressing the minus superscripts and the time variable j on the right-hand side. All right, so let's take a look at some simulation runs. Delta t in the first simulation is 1/10 of a second. We're also assuming 50% process noise assumption factor. We talked about that in the last video. For mass, I'm taking 1 kilogram, or taking a light spring constant of 1 Newton meter, a medium damping factor of 5 Newton seconds per meter. And here's what we get for our TME plot. You can see that with these parameters and that sampling period, we're actually getting pretty close hugging of the truth by our estimates. The truth again is in blue, the estimates are in black, and measurements are in red. You can see that the truth in the velocity model is actually bouncing around a bit. That's because we are assuming there's some real process noise in the truth itself. It's only 50% of what we're assuming it to be in our model. We're trying to be conservative with the model, but nonetheless we're actually able to hug the truth pretty closely. And here's the sawtooth plot. You can see it rises up to a certain transient level then, and then for steady state it settles out after about 2 seconds or 20 Kalman cycles. Note the scale on the variance here. Again, this is just position variance. Now we're going to change only the time sampling delta t. So we're now an order of magnitude longer in sampling period. It's 1 second as opposed to 1/10 of a second. Everything else stays the same. And what we get is obviously much more process noise in the velocity and correspondingly also in the position state. And the estimate in velocity, as you can see, is having a harder time keeping up with the process noise and velocity. And that ripples into the position as well. So you can see the sawtooth plot is pretty much the same sort of thing as it was before. There's really no settling back down. It gets past the transient and stays up there pretty high. And the amount of variance here you're seeing in position is an order of magnitude more uncertain than it was in the previous simulation. So delta t does matter. That's the moral of the story here. Okay, so let's do a vector check. Where are we? We've looked at the damped harmonic oscillator and how the discrete model depends on the continuous model. And also, we've taken a look at the results of some simulations. Now, I haven't gone into the code itself. You can take a look at the code. It's out on GitHub. Have at it. Experiment with it, as we mentioned before. So what's next? Next video, we're going to present some exercises for you to solve. And then in the video after that, we'll present the solutions. So that's all for today. Have a good day. We'll see you in the next video.